what we're going to see next is what I refer to as the symphony of spheres. And this is another one of these jaw-dropping moments. And what we have is a sphere of water about 3 inches in diameter. It's attached to a wire frame with about 1.5 inch diameter bubble of air injected into the center of the sphere. And then there's going to be some delightful dynamics that happen between the sphere of water, the bubble and the bubble in the middle. So let's go ahead and see what happens here. Here we have our sphere with the air bubble in the middle. And as we inject more air into the air bubble, it drives these delightful oscillations, as you can see here. And these oscillations make standing waves on this air bubble inside. And here's a slow motion playback showing the air being injected and the standing waves in this center bubble. So this is similar to the large sphere oscillations that we saw, but it's the inverse system. It's a low mass bubble surrounded by a high dense medium and the oscillations that are being driven in this system. And this would be difficult to observe in other than a weightless environment, because with bubbles this large, they would separate out from the fluid rapidly. So here we see again bubbles being introduced in the oscillations, but look what you have left in the wake here. You see little droplets, solid droplets of water bouncing around inside of the bubble that's inside of the sphere. So that's why I call this the symphony of spheres. You've got droplets in a bubble in a sphere, and this led us to just directly injecting droplets inside of the sphere. And here you see the Teflon cannula going into the bubble, injecting a whole series of small droplets in this sphere. And these droplets could be anywhere from 1 millimeter in diameter up to maybe 8 millimeters in diameter. And they ricochet and bounce around in this bubble, sort of like a three-dimensional billiards game. And the resultant dynamics is just amazing, where you see collisions between these droplets and the wall, and collision between droplet to droplet. And sometimes there is an amalgamation, a transfer of fluid between these interfaces. Sometimes there isn't. Here we see a droplet bouncing around, and it might undergo 5, 6, 7, 8 collisions before there's a transfer across the interface, and that transfer imparts momentum into the droplet and it sends it zooming off, and then it'll undergo another 4, 5, 6, 7, 8 collisions before there's another transfer, a mass across the interface. And so what's happening here? What's driving this? There's a lot of questions which I still find baffling. Just look at the fate of these little droplets as they bounce around. Here's another droplet being injected, and it will suffer mass transfer on the first collision. Now we're going to see a slow motion playback of that, where this droplet is going to touch the inner wall of the bubble, and then you see a mass being driven from the droplet through the interface into the surroundings. And if you look at your surface chemistry, you'll realize that the pressure inside of a small droplet is greater than the pressure inside of a larger droplet. So the mass transfer is going to want to be from the droplet into the surroundings. So that all makes sense. And the fact that this pressure differential drives the water, there's a mass exchange that makes momentum exchange, and it acts like a little rocket, and it propels the droplet away from the surface. So all of that seems to make pretty good sense. But why will these droplets undergo multiple collisions before there is this transfer across the interface? That's what I find so baffling. And now here we see another example of a droplet that is rolling on the interface, and the radial acceleration from circular motion creates its own artificial gravity, so to speak, and it will sit there and just roll around and around and around on the inner surface of this bubble. And they may roll for as much as 30 to 40 seconds, and then all of a sudden there'll be a mass transfer event. So again, what's governing the dynamics here? Why does this droplet roll and roll and roll, and then all of a sudden decide to transfer some mass? And here we see this droplet rolling and rolling and rolling. It's creating its own artificial gravity, which holds it in contact to the inner surface of this bubble. And then after doing this for some time, there's a transfer of mass, which you see there, and it jets the droplet off of the surface. Here we see another droplet rolling. This time it's rolling perpendicular to the field of view, so it's going in and out of the depth of the picture here, and it rolls and rolls and rolls until there's a mass exchange, and then it gets blasted off of the surface. And so a rhetorical question is this drop rolling like a ball rolls across a carpet, or is this drop scooting like a hockey puck would scoot on a ice rink? And so what do you think's happening here? We'll see later on the answer to this question. Here's another example of injecting drops into one of these bubbles where the whole bubble is expelled from the droplet. Now here we're using food coloring in the droplets when we're injecting them to look at the flow of fluid from the droplet into the surrounding sphere. And let's see what that fluid flow looks like. What you see is when there is a mass transfer, it generates a little vortex ring that expands into the surrounding fluid. And I guess this isn't surprising, since we've already seen that when a droplet gets introduced from the outside of a sphere, it makes a vortex ring. And so having a droplet get introduced from the inside of a bubble, it's expected that it'll also make a vortex ring. Now here we have a droplet made with tracer particles. These are the 5-micron diameter tracer particles. And look at this droplet as it's rolling around on the inner surface of the bubble. And you can actually see that it is rolling like a bowling ball rolls rather than sliding like a hockey puck. However, if we look at this droplet, it too is rolling like a bowling ball. However, its direction of rolling is 90 degrees to the actual direction of circular motion for the droplet. So from this, I conclude that the droplet is really sliding like a hockey puck. However, there's some initial rolling motion when you inject the droplet into the system, and it's making the droplet roll. However, the rolling is not in synchronization with the rate at which it is moving in a circle. At least that's how I'm presently looking at this. Here we have another droplet with tracer particles, and it's going to rapidly get absorbed through the interface. And the interesting thing here is how a little cloud, it looks like a little polar cloud of tracer particles forms around the outside of this bubble due to the rotation forces. It looks just like a little weather system you would see forming on a planet.